Welcome back to my class in Integral Calculus. Today we will take up the definite integral. First, we differentiate the indefinite integral from definite integral, and the difference is very slight. This notation is what is known as the indefinite integral, where this is the integral sign, this is the integrand, and dx indicates that we should integrate the function f of x with respect to x. And this notation is what is known as the definite integral. We have the integral sign, the integrand f of x, and dx again indicates that the variable of integration is x. And you can see that the difference is very slight between the indefinite and the definite integral. These numbers a and b are called the limits of integration of the definite integral. In particular, a is called the lower limit of the integral, and b is called the upper limit of the integral. And these limits of integration make the difference between the indefinite and the definite integral. When evaluating a definite integral, you should treat it initially as indefinite integral, which means that you initially ignore the limits of integration a and b, and you proceed with evaluating the given integral as though it is an indefinite integral. And in evaluating the indefinite integral, you now apply one or more of the integration rules or one or more of the techniques of integration. And how do we evaluate? After you have evaluated the indefinite integral by removing initially the limits of integration, how do we evaluate now the definite integral? Now, suppose in evaluating the indefinite integral by removing the limits of integration a and b, the function that you get is, the answer that you get is a function of x we denote by f of x. Another difference between the indefinite and definite integral is that after evaluating the given integral without the limits of integration, we do not need the constant of integration, capital C, usually denoted by capital C. Indefinite integral, after evaluating the indefinite integral by removing the limits of integration, we no longer add the constant of integration, capital C. So this function capital F of x is the answer after evaluating or after integrating f of x with respect to x. And it is this function that we evaluate using the limits of the given definite integral from a to b. And in evaluating, you start always with x equals b. Evaluate the given function capital F of x when x equals b minus, it's always minus, evaluate the given function, evaluate the function f of x. This is not the given function, this is the solution of the integral of f of x dx, minus evaluate the function f of x when x equals a. And that's basically the process for evaluating a definite integral. Again, the first step is you evaluate this integral as though it is an indefinite integral. You initially ignore the limits of integration and integrate the resulting indefinite integral, applying one or more of the integration rules or one or more of the techniques of integration. And supposing the solution that you get for the integral of f of x with respect to x is capital F of x, we no longer add the constant of integration c. we evaluate this function f of x according to the limits of the given definite integral. That is, we evaluate the function f of x from a to b, always starting with evaluating the function f of x when x equals b. And you get f of b minus, it's always minus the result when you evaluate the function f of x when x equals a. We now take some examples. For our first example, consider the definite integral, the integral of x minus 2 dx, to be evaluated from negative 1 to positive 1. We integrate this linear function x minus 2 and we apply the power rule, where the exponent of x here is 1, and by power rule, the integral of x is plus 1 to the exponent of x, that's 2, and divide x squared by 2. So the integral of x with respect to x is x squared over 2. Minus the integral of 2 with respect to x. If there is an x beside 2, its exponent must be 0. X to the 0 is 1. And we apply the power rule, plus 1 to 0, the exponent of x to the 0. You get x, multiply by 2 and divide by 1. So the integral of minus 2 with respect to x is minus 2x. If this is an indefinite integral, we should add a constant of integration c. But this is a definite integral, so there is no need to add a constant of integration c. And we now evaluate this result, the integral of x minus 2 with respect to x, from negative 1 to positive 1. In the discussion earlier, this is the capital F of x, the function capital F of x, x squared over 2 minus 2x. And we find the value of this expression when x is 1. When x is 1, you get 1 squared over 2 is 1 half. Minus, when x is 1, minus 2 times 1 is minus 2. And this is the value of this function x squared over 2 minus 2x when x is 1. And from this, we subtract minus the value of this function f of x when x equals negative 1. When x equals negative 1, you get negative 1 squared is positive 1 over 2, 1 half. Minus 2 multiplied by x, x is minus 1. And minus 1 times negative 2 is plus 2. And we simplify, you can see that we have 1 half minus 1 half is 0. And this is minus 2, negative times positive is negative 2. Thus, we have minus 2 is negative 4. And that is the integral of x minus 2 dx for x equals minus 1 to x equals positive 1. For our next example, consider this definite integral, the integral of x into the x dx, to be evaluated from 0 to 2. And you can see that this is not readily integrable by using any one of the integration rules. So we apply one of the integration techniques. In particular, we use the integration by parts, where we let u equals x. And we let dv equals e to the x. From u equals x, we differentiate both sides. Derivative of u with respect to u is 1 multiplied by du. And derivative of x with respect to x is 1 multiplied by dx equals dx. And for dv equals e to the x, we integrate both sides. The integral of dv is v. And the integral of e to the x is e to the x. By integration by parts, the given integral is equal to uv minus the integral of v du. We replace u and v with their values. U is x and v is e to the x. So the first term is x times e to the x. Minus the integral of v e to the x du is dx. The integral here should have the limits, the given limits, 0 to 2, but I have omitted it. Since we are not ready to evaluate, we have to first find the integral of e to the x dx before we evaluate all these terms, this difference from x equals 0 to x equals 2. The first term is as is, x times e to the x minus the integral of e to the x with respect to x is e to the x. So we have integrated already the second term. There is no need to add a constant of integration. We now evaluate this answer. This is now the integral of x e to the x with respect to x, and we now evaluate this. This is the function capital F of x, and we evaluate this from x equals 0 to x equals 2. And we start from the upper limit. When x is 2, you get 2 multiplied by e to the power 2, or 2 times e squared. Minus e, x is 2, or e to the 2, to the second power, or e squared. Now we evaluate the same expression when x is 0. Minus, it's always minus. When x is 0, you have 0 multiplied by e to the 0. E to the 0 is 1, but multiplied by 0 is 0. Minus e to the 0, x is 0, and e to the 0 is 1. So we write minus 1. And we simplify, we have 2e squared minus e squared and 0 minus 1 is negative 1 multiplied by negative 1 is positive 1. And this is the answer for the integral of x e to the x dx evaluated from x is 0 to x equals 2. For our example 3, consider the following definite integral, the integral of sine 3 theta d theta to be evaluated from theta equals 0 to theta equals pi over 2. First, we have to convert the given integrand with an angle whose coefficient is 1. The coefficient of the angle here, the variable angle here, theta, is 3. So we let u equals 3 theta. And we are using integration by substitution, simple algebraic substitution. We differentiate both sides. Derivative of u is du. And derivative of 3 theta with respect to theta is 3 d theta. And in the given, we have d theta, so we solve for d theta from du equals 3 d theta by dividing both sides by 3. If you divide the right hand side by 3, you get d theta equals, you also divide the left hand side by 3, you get du over 3. And in the given integrand, we replace 3 theta with u, and d theta we replace with du over 3. And the given integral is equal to, you can initially remove the limits of integration. You simply write integral of sine 3 theta is u, or sine u. Multiply by d theta is du over 3. And we apply one of the integration rules. 1 over 3 is a constant, so we can take that out of the integral sign. 1/3 1/3 times the integral of sine u with respect to u. Now you can see that the coefficient of the angle, the angular variable u here is 1 and is now readily integrable by applying the integral of one of the trigonometric functions, the integral of sine u. And the integral of sine u is negative cosine u. This is 1/3. Times the integral of sine u is negative cosine u. Again, there is no need to add a constant of integration, and we now evaluate this from 0 to pi over 2. But before you do the evaluation, we replace u with its value. U equals 3 theta. We have 1 over 3 multiplied by negative cosine. U is 3 theta. Evaluate from 0 to pi over 2. Equals 1 over 3. Again, you can take the negative sign out. Multiply negative by 1/3, negative 1/3. We evaluate cosine 3 theta now, beginning with theta equals pi over 2. Pi over 2 multiplied by 3, you get 3 pi over 2. Cosine of 3 pi over 2. minus, it's always minus. Evaluate cosine 3 theta when theta is 0. When theta is 0, multiply by 3 is 0. So we write here minus cosine of 0. And cosine of 0 and cosine of 3 pi over 2 we find using our calculator, but be sure to write to have your calculator in radian mode, because 3 pi over 2 and 0 are in radians and not in degrees. So put the mode of your calculator in radians when you evaluate cosine of 3 pi over 2 and cosine of 0. We now find the value of cosine 3 pi over 2 using our calculator, whose mode should be in radians. We also find the value of cosine 0 using our calculator, and the calculator should be in radian mode. So the given integral of sine 3 theta d theta to be evaluated from 0 to pi over 2 is equal to negative 1/3 multiplied by cosine of 3 pi over 2. Cosine of 3 pi over 2, if you will find that using your calculator, is equal to 0. Minus cosine of 0. And cosine of 0, if you will use your calculator, is equal to 1. And this simplifies to 0 minus 1 is negative 1, multiplied by negative 1/3 is positive 1/3. And 1/3 is the integral of sine 3 theta d theta evaluated from 0 to pi over 2. We now take an example to apply definite integration to finding an area bounded by curve and lines whose equations are given. For our first example on the application of definite integration, consider the following problem. Find the area bounded by y equals x squared, the x-axis, and the lines x equals 2 and x equals 5. This equation is a quadratic equation in x, and it is of the following form. This equation is of this form, and the graph of this equation is a parabola. When you see an equation that is quadratic in x but linear in y, you are sure that the graph is a parabola that opens either upward or downward. And if the coefficient for p is positive, then the parabola is open upward. Or if p is positive greater than 0, the parabola opens upward. Again, when P is positive, greater than 0, the parabola is open upward. And if P here is negative, less than 0, the parabola is open downward. And the parabola has a vertex. The vertex is at the point HK. Since the coefficient of x squared here is positive 1, that means your P is, your 4P is 1. This implies P is equal to 1 over 4. And 1/4 is positive, greater than 0. Therefore, the graph of this equation is parabola that opens upward. And you can see that x squared can be written as x minus 0 squared, and y can be written as y minus 0. So the vertex of this parabola is at the point 0, 0, or the origin. And if you have an equation that is quadratic in x and linear in y, and the vertex is at the origin, the y-axis is the axis of symmetry, which means that the y-axis will divide the parabola into two equal parts. But if the vertex of the parabola is not at the origin, it is at the point HK, where H and K are not both 0, then the axis of symmetry of the parabola would be parallel with the y-axis. Now, these equations, x equals 2 and x equals 5, are already given. They are given as lines. And in particular, these are vertical lines parallel with the y-axis. This equation x equals 2 is a vertical line parallel with the y-axis and will pass through the x-axis at the point x equals 2. This equation x equals 5 is also a vertical line parallel with the y-axis and will pass through the x-axis at the point x equals 5. And the area that we want to find is bounded by the part of the x-axis. Now we are ready to sketch the graph of the required area. We start with the lines x equals 2 and x equals 5. Locate these points on the positive x-axis. And I have used a 2-unit intervals, 2, 4, 6, and this is 5. Now, the lines are vertical. The line x equals 2 is a vertical line. It will pass through the x-axis at x equals 2. The line is vertical parallel with the y-axis. The line x equals 5 is also a vertical line parallel with the y-axis and passing through the x-axis at the point x equals 5. Now we sketch the graph of this quadratic equation in x, which is a parabola, with vertex at the origin. And we know that the parabola is open upward. So from this point, if the parabola is open upward, this point, the origin or the point 0, 0, the vertex of the parabola is the lowest point on the parabola. And from this point, the graph of y equals x squared will go up because the parabola is open upward. And the graph is symmetric with respect to the y-axis. That means y divides the parabola into equal parts. The part of the parabola to the right of the y-axis and the part of the parabola to the left of the y-axis. But since our lines are to the right of the y-axis, we confine the graph of this equation y equals x squared to the right of the y-axis. That is, we only sketch the graph half of the parabola. The part of the parabola to the right of the x-axis. You can see that the parabola intersects the line x equals 2. And we find this point of intersection of the parabola y equals x squared and x equals 2. And at this point, we already know that x equals 2. And when x is 2, the value of y is 2 squared. So this point has coordinates 2, 4. And this point on the y-axis is 4. And this point has coordinates x is 2 and y is 4. At this point, the value of x is 5. And when x is 5, the value of y is 5 squared. So this point of intersection of the line x equals 5 and the parabola y equals x squared has coordinates 5 and 25. X is 5 and the y is 25. Now, the area that we want to find is bounded by this part of the parabola. The x-axis, it's not the entire x-axis, it is this part of the positive x-axis. The area that we want is bounded by part of the line x equals 2. It is this part of that line x equals 2. And part of the line x equals 5, which is this. And the shaded portion of the graph is the area that we want to find, and we will find this area using definite integration. Now, there are two ways by which we can find the area of this region bounded by this part of the parabola, this part of the x-axis, and this part of the line x equals 2, and this part of the line x equals 5. The two methods have to do with taking rectangular elements from the area. The first method is by taking vertical rectangular element, and the other method is by taking a horizontal rectangular element. In this method 1, we take a vertical rectangular element. You draw a rectangle anywhere in the region, in the area that is required, and the rectangle should go from this part of the x-axis to this part of the parabola. And we find the area of this rectangle. And from plane geometry, we know that area of rectangle is equal to the length multiplied by the width. If you take a vertical rectangular element to find the area of the region, the width is equal to the differential of x. Again, if you use the first method by taking vertical rectangular element, we apply the formula for area of rectangle. We draw a rectangular element and we find the area of the rectangle using the basic formula length times width. But if you take a vertical rectangular element, the width of the rectangle is always the differential of x. If x in your given problem is the independent variable. And we find the length, the longer dimension of the rectangle, which is the length from this point on the x-axis to this point on the parabola. And the length is, this is the length of the parabola, and it is the difference between the value of y at this point minus the value of y at this point. At this point on the parabola, the value of y is given by x squared minus the value of y at this point. So the length of the parabola is the difference between two y values. Always start with the value of y at the upper base of the rectangle. The value of y at this upper base of the rectangle, which is a point on the parabola, is given by x squared minus the value of y at this lower base of the rectangle. And it is a point on the x-axis, so y is equal to 0. We know that any point on the x-axis has ordinate or y equal to 0. And so the length is simply x squared. And the area of the rectangle, the area of this rectangular element is now length multiplied by width. The length is x squared multiplied by dx, the width. Area of this rectangular element is length multiplied by width, x squared multiplied by dx. And after you have found the area of the rectangular element in your graph, you now integrate this expression. Integrate the expression x squared dx, or integrate x squared with respect to x. But the area that is required is from this line, this part of the line where x is 2, up to this part of the line with the equation x equals 5. That means we can draw any rectangular element from this point x equals 2 to x equals 5. Or you can draw all the rectangular elements from x equals 2 and x equals 5. And you get the sum of the areas of these rectangles and you get the required area. But we will not do that. Instead, we will integrate. Integrate, that means we combine all the areas of the rectangles. And each rectangle has an area of x squared dx. And the rectangles can be drawn from x equals 2 to x equals 5. Therefore, we evaluate this expression x squared with respect to x from x equals 2 to x equals 5. And the value of this definite integral is the required area. We now evaluate. Treat this as indefinite integral. Integrate x squared with respect to x by applying power rule. And the integral of x squared by power rule plus 1 to 2, you get x cubed and divide by 3. And we do not add the constant of integration, but instead we evaluate x cubed divided by 3 from x is 2 to x equals 5. And this is equal to 1/3. Instead of evaluating x cubed over 3, you may write 1/3 times evaluate x cubed from 2 to 5. We start with the upper limit of integration. When x is 5, you get 5 to the power 3. 1/3 is already out. X is 5, you get 5 to the power 3, that's 125. Minus, when x is 2, you get 2 to the power 3, that's 8. And 125 minus 8, that's 117. Multiply by 3, that's 117 over 3. And we do not know the units in this problem, but we know for sure that area is in square units. So we write 117 over 3 is square units. And this is the area bounded by this part of the parabola, this part of the x-axis, and this part of the line x equals 2, and this part of the line x equals 5. And we will now check this answer using the second method by taking a horizontal rectangular element. We solve the same problem, that is, we find the area bounded by this part of the parabola with the equation y equals x squared, with vertex at the origin, bounded by this part of the x-axis, bounded by this part of the line x equals 2, and bounded by this part of the line with the equation x equals 5. But this time we will use the second method, that is, we take a horizontal rectangular element. That is, the rectangular element would be parallel with the x-axis. Earlier we took a vertical rectangular element, vertical rectangle that is parallel with the y-axis. This time the rectangular element would be parallel with the x-axis, and so it's called horizontal rectangular element. Now, if you draw a rectangular element at this part of the area, you can see that the bases of the rectangle have points on this line x equals 5, and this point on the rectangle is a point on the parabola y equals x squared. But if you take a horizontal rectangular element here, you can see that the bases of this horizontal rectangular element have points on this line and on this line. That is the ends of this rectangular element here on this part of the area is on the parabola and on the line. But if you take a horizontal rectangular element here, the ends of the rectangular element have points on this line and on this line. And actually you will have this similar rectangle, horizontal rectangular element, if you draw rectangles, horizontal rectangles from this point up to this point. If you draw horizontal rectangular elements from this point up to that point, the points, the ends of the bases of the horizontal rectangular elements have points on the parabola and on the line x equals 5. But if you draw horizontal rectangular elements from here, from the x-axis up to this point, the bases of the rectangular elements have points on the line x equals 2 and the line x equals 5. So we will divide this area into two areas. We will call this A1 and this area A2. And the total area is equal to A1 plus A2. And we start with A1. Again, we find the area of this rectangular element taken in A1. And the area of the rectangle, by basic formula, is length times width. In the first method where we took a vertical rectangular element, the width is equal to the differential of x. But in method 2, if you take a horizontal rectangular element such as this rectangle, horizontal rectangular element, the width is equal to this dimension, the shorter side of the rectangle is equal to the differential of y or dy. And we find the length of this rectangle. The length of this rectangle is equal to this length minus this length. Again, the length of this rectangle taken in A1 is equal to this length minus this length, or 5 minus 2 is equal to this length. This length of the rectangle is equal to 5 minus 2. Or 3. So the area of this rectangular element by this formula, length times width is equal to 3 multiplied by dy. And we integrate this expression. That is, when we integrate, we are actually getting the sum of all the horizontal rectangular elements from this point up to this point. But at this point, the value of y, now the variable of integration is y. So we integrate this with respect to y, and we evaluate this for values of y from 0 up to 4. We take horizontal rectangular elements from the x-axis where y is 0 up to this point where y is 4. And we integrate 3 with respect to y, we get 3y. And we evaluate 3y from 0 to 4. When y is 4, you get 12. 3 multiplied by y is 4 is 12. Minus when y is 0, 3 multiplied by 0 is 0. And 12 minus 0 is 12. And that's the area A1. Now we find the area A sub 2 denoted by A sub 2. Again, we first find the area of this horizontal rectangular element by the basic formula length times width. Where the width for horizontal rectangular element is always dy, or the differential of the dependent variable. In our example, the dependent variable is y. And we find the length of this rectangular element. It's the same method that we use when we find the area of this rectangular element from A1. The length of this rectangle is equal to the value of x at this point is equal to 5 minus the value of x. This is the value of x, and we can find the value of x. You can see that this point is a point on the parabola, and the parabola has equation y equals x squared. And from y equals x squared, you solve for x. So you can get this value of x at this point, which is actually the distance from the y-axis to this point, and that is x. From here, x equals the square root of y. So this length is equal to square root of y. At this point, from this point up to the y-axis is 5. So the length of this rectangle is 5 minus square root of y. And the area of this rectangular element is now length multiplied by width, 5 minus square root of y. Multiplied by the width differential of y, or dy. And we integrate this expression, that is, we actually get the sum of the areas of the horizontal rectangular elements from this point up to this point. That is, we evaluate this expression with respect to y from y is 4 to y is 25. And to integrate square root of y, we apply the power rule. If you remove the radical sign, square root of y is equal to y raised to 1/2. I will initially remove the limits of integration. The integral of 5 with respect to y is 5y. And we integrate minus the integral of y raised to 1/2 with respect to y. We apply the power rule. We add 1 to 1/2. 1/2 plus 1 is 3/2. Minus y raised to 3/2. Divide by 3/2 or multiply y raised to 3/2 by the reciprocal of 3/2, you get 2/3. And it is this expression that we evaluate from y is 4 to y equals 25. First, we evaluate this expression for y equals 25. When y is 25, you get 5 times 25, that's 125. Minus, this is y is 25, 25 to the power 3 halves. You can use your calculator, or you take the square root of 25 is 5, and 5 to the power 3 is 125, and multiply by 2, 250, divide by 3. Minus, we evaluate this same expression when y now is 4. When y is 4, we get 5 times 4 is 20. Minus 2/3 times 4, y is 4 raised to 3 halves. 4 raised to 3 halves, you can use your calculator, 4 to the power 3 over 2, or square root of 4 is 2 to the power 3. 2 to the power 3 is 8. Multiply by 2 is 16 over 3. Minus 16 over 3. We simplify 125. Multiply 125 by 3 over 3. So that common denominator is 3. 125 multiplied by 3 is 375. 375 minus 250 is 125. $375 minus 250 is 125 over 3. Minus, now multiply 20 by 3 over 3, you get 60 over 3 minus 16 over 3. Common denominator is 3. And 60 minus 16, 60 minus 16 is 44 over 3. And 125 minus 44 is 81 over 3. So the area A sub 2 from this point up to this point is 81 over 3. And we now get the total area by adding A1 and A2. We now find the total area A, which is the sum of A1 and A2. And the sum is the required area. Earlier we obtained 12 square units for the area A1. And to 12 we add the second area A2, and earlier we obtained 81 over 3 for the second area A2. And we multiply 12 by 3 so that we have a common denominator of 3. And 12 multiplied by 3 is 36. And 36 plus 81 is 117. And you can see that we obtained the same area of 117 over 3 using horizontal rectangular element. But you can also see that it's easier to obtain the required area using a vertical rectangular element, in which you do not have to divide the required area into two areas, unlike in the second method where we took a horizontal rectangular element. We have to divide the required area into two areas, A1 and A2. And the choice between method 1 and method 2 depends on the graph, the area that is shown in the graph. And that completes our lesson, Introduction to Definite Integration. And for your practice, please try the following exercises. Number 1, evaluate the following definite integrals. A. Integral of x squared plus x minus 1 with respect to x. Evaluate from 1 to 2. B. Integral of cosine 2x with respect to x. And evaluate from x equals minus pi to x equals pi. And when you evaluate this integral, you put the mode of your calculator in radians, because pi, minus pi, and pi are in radians. And C, evaluate the integral of x ln x dx from x is 1 to x is 3. For letter C, you have to make use of an integration technique. For letter B, you have to make use of substitution. And letter A can be directly integrated by using power rule. And number 2, find the area bounded by x equals y squared, the x-axis, and lines x equals 9 and x equals 25. Letter A, take vertical rectangular element. And for you to check your answer, you must get the same answer for letter B when you take horizontal rectangular element. The graph of this, now this is a quadratic equation in y. And a quadratic equation in one variable, either x or y, the graph is a parabola. So the graph of this is a parabola, but the axis of symmetry, the line that divides the parabola into two, is the horizontal axis or x-axis. And this equation is actually of this form. This given quadratic equation in y is of this form. This is the general form of a equation of parabola with vertex at the point HK, with axis of symmetry, the horizontal axis or a line parallel with the horizontal axis or x-axis. If you get a p that is greater than 0 or positive, the parabola is either the parabola is open to the right. Again, if you get p that is positive or greater than 0, the parabola is open to the right. If your p is less than 0 or negative, the parabola is open to the left. Direction of the arrow goes to the left. And you can see, obviously, from the given that the vertex of the parabola is at the point 0, 0 or the origin. And that's our lesson for today on the introduction to definite integration. If you have question about the lesson today, you ask your question in the comments below. And thank you for joining me in my class today in integral calculus.